Okay, everybody, welcome to another one of our Fall Communication Systems Laboratory seminars. And today we're really excited to have Peter Kazakov, who's going to be speaking to us today from Sofia. And he's working at the Institute of Mathematics and Informatics at the Bulgarian Academy of Science, along with Sanka. And they've been designing some CRCs specifically for polar codes. And we got really interested in their work when we were comparing convolutional codes with CRCs to polar codes with CRCs, both under list decoding. So Peter received his master's in mathematics from Sofia University in Bulgaria and his PhD from the Technical University of Delft. And his PhD thesis is in the area of CRCs and spherical codes. So he's really the right person to talk to us about CRCs. And he's been working at a variety of software companies, including NXP Semiconductors, ST Ericsson, SAP, and currently at Scale. So anyway, without further ado, Peter, why don't you go ahead and tell us the story of CRC codes for polar codes? Thank you.
Okay, thank you. It is a big pleasure to do this presentation for me. Today I will talk about the CRC selection of decoding of CRC-polar codes. And I'll elaborate on some further results and some future plans. So what will this presentation consist of? First, I will talk the publications that I will base this presentation. We'll make introduction to CRC codes. Then we'll speak about the polar codes and the decoders. Next, quite importantly, we'll define the optimization criteria, what we're looking to optimize, what kind of problems we had with the algorithms, how we approach them, what kind of results we have from the two papers that I will present, and some ideas, future ideas, what can be improved on CRC codes. So this paper contains, this presentation contains materials mostly from two papers. So one is our joint work with Sanka, CRC selection of decoding of CRC-polar concatenated codes. It is published in BCI in 2019, and also presentation with also work with Sanka and Miroslav Dimitrov about some comments on CRC selection of 5G specification. This paper is present only in archive. It's still not published. We're looking on a suitable place to publish it. Okay. First, to make the note that we're talking about the binary codes, and for CRC code we have this construction when to the information block of k binary digits. We are adding p. We are adding a block of p parity bits, and in this way, at the end, we verify whether the word is transmitted correctly. The main question is how do we form this block of p bits, and the general approach is for CRC codes that we are using its generated polynomial g of x of degree p. So we are making x at degree p multiplied by I of x, and then we are making modulo g of x. So the most important characteristic of polynomial is of polynomial g of x is its order, and the order is defined as the minimum number such that x at degree m is comparable with one model g of x. So basically, there are no sense to generate a polynomial g of x above its order, because at that point we are already running the risk to have minimum distance of 2, and this is not very nice. You can achieve minimum distance of 2 if you just have a polynomial x plus 1, if g of x is x plus 1.
So Peter, can I just ask this question? This is the question we were talking about before. Is it the case that every polynomial has an order, so that there is some?
Yes.
Okay,
yes.
Thank you.
Every polynomial has an order, and of course, for g of x, we have also some assumptions. One assumption is the degree p, and the other assumption is that it is not divisible to x. So it finished to plus 1. The last bit is 1. So g of x is a polynomial dividing x and c plus 1, and this is for cyclic code. And in reality, we are not using the cyclic codes. We are using shortened cyclic codes, and the shortening is actually any n minus p subcode c of c prime is obtained by shortening of c prime in nc minus n positions. I will show you on a matrix how this one is performed. And shortened codes are usually not cyclic. However, they share the same encoders and decoders. So the process of encoding and decoding is absolutely the same. What we can say here, perhaps I had to put a few definitions more. A polynomial that has an order of 2 to the power p minus 1 is called primitive polynomial. It is also quite important subclass, and it has a minimum distance of 3. So basically, when we investigate these polynomials g of x, we have to investigate all possible polynomials, and with the increase of p, here I put r, but with the increase of p, this is getting quite a large number of polynomials. Actually, we omit reciprocal polynomials, and we still have 2 at the power p minus 2 possible choices. And with ai and bi, we denote the weight distribution of the code c and the dual code c. When we investigate what is the optimal polynomial for certain n, for certain length, the most important characteristic is the function of undetected error probability, PUD. This was part of my PhD thesis, and what we have here as expression is that this is equal to one sum. Here a0 is 1. We have nothing to, we cannot change it. A1, A2 up to d minus 1 are zeros. And when the noise, here epsilon is noise, tends to 0, actually the most important characteristic is AD. So to find for certain length, for given length, the optimal polynomial, we first have to find the maximum among all polynomials. We have to find the maximum d, and among all polynomials that have this maximum d, we have to find the minimum ad.
Excuse me, I would like to clear that D means minimum distance.
Yes. The D is a minimum distance. I didn't put it here. We'll talk about the complexity of this problem later on. However, normally
Did we just have a freeze?
we are not looking for optimal certain interval. And when we are looking for optimal solution for certain interval, we can optimize on the maximum SG. And here is example that the interval is from p plus 1 to m. And when we are trying to optimize on interval, we are looking for maximum of this SG. And now, what is the problem complexity? Like I said, we have two at the power p minus 2 polynomials g. For each of these polynomial, we have to investigate the interval from p plus 1 to its order, and the order is less than 2 at the power p. And for each of these combinations, we have to calculate the distance distribution of the dual code. And while we are calculating first the distance distribution of the dual code, here important part of the algorithm is coming. We can define h of x in this way, and then we have the matrix H. Matrix H is the generator matrix for the dual code, and it has only p number of rows. So to count the distance distribution, we have to make all the combination to the power p of this rows, and for each combination we have to count what is what is the weight of this vector, how many elements with ones we have in this vector. When we are shortening the code, we are starting from the right side of this matrix, and shortening by one position means to cut the upper right column, shortening by 2 positions, again, the 2 upper right columns, and so forth. Once we calculate the dual distance distribution, we can to calculate the dual distance distribution, we can use the gray code to go through all combinations, 2 to the power p minus 1. And when we calculate the weight, we can use the Mach-Williams transformation for distance distribution to get the distance distribution of the normal code. Here we have one bonus point. If for any reason we do a miscalculations, if we're not counting correctly, it is almost for certain that this Mach-Williams transformation will result in non-integer numbers, and we will see that we are on a wrong way. So we will see that we didn't count properly. Do you have questions on CRC codes? Because I will continue with polar codes after that.
Does anybody want to ask a question? I would like to encourage that.
Okay. Let's continue with the polar codes. Actually, the polar codes are quite good area to to experiment with different CRC codes. They're described by Staudt in 2002 and later independently by Arikan. Actually, the paper of Staudt was in German and it was highly unnoticed at that time. And Arikan is really the one that popularized the polar codes. They're based on recursive linear construction. And their encoders and decoders have a very good complexity and n times log n. They're first probably capacity achieving codes. Channels are polarizing in infinity, and that's why they get their name polar. And the concept is somehow similar to FFT transformation without the multiplication part. So for polar code, we have two parameters. We have n and k. N is a degree of 2. And k are the number of information bits, and we have a number of frozen bits. They're based on recursive definition with a canonical product, like you see here. The big problem for polar codes is the decoding of polar codes. There are various papers on this subject. Initial one is Arikan, a method for constructing capacity achieving codes. Then we have successful cancellation, fast SSC decoding. One paper of Pascal Guéard, not sure whether I pronounced the names correctly, Thibault and Gross. Also quite interesting. ML, SSC decoding, belief propagation, and list-based decoding. Actually, what we'll talk about in this presentation is list-based decoding. It is introduced by Tao and Vardy, 2011, and then they have one other paper, 2013, I think. For successful cancellation, for instance, is two-step decoding approach, greedy algorithm. Each element has a computational tree, but it still has some satisfactory performance or short and moderate block lengths. So list decoding, the initial approach of Tao and Vardy was up to L decoding paths and contains a CRC16 verification, use of Gini to filter out the bad choices. And of course, it has a price. We add 16 more bits to the polar code. So it is the price with any CRC code. We need to find the right balance. If it is if the CRC code is too small, perhaps the function of undetected error will be higher. If the CRC is too big, perhaps we can get unnecessary errors in the CRC code, and there should be some balance on the size of CRC code, the number of the minimum distance that it has, and the number of information bits. So in our first paper, what we decided that this was the attempt to attack the case with 24 bits. We are using 2 to the power p minus 2 polynomials that are generating code C, and we have that the order is less than 2 to the power p. We are shortening them in a number of positions, and we are using the gray code to count the number of words. So this algorithm works quite nicely with nowadays normal computer for dimensions for p equal to 16, 17, 18. But with the increase of the complexity, it gets slower and slower. The nice part of our standard of our definition for optimal solution is that this minimum distance, if we look at the minimum distance as a function of c, it is a monotonic function. So if for two values of m and m1 it has the same minimum distance, it is clear that all values between m and m1 are with this minimum distance, and we don't have to look further. So we might some sort of slight modification of this algorithm to divide the interval by 2 to check the value, and if it is equal to one of the other values to say, okay, we don't have to look further in this interval. If it is different, to say, okay, we have to do the next split somewhere in between. And why I say modification? Because the minimum distance is high, for instance, for p equal to 24. The minimum distance is high, let's say, to some values around 512. Let's say that there we have minimum distance of 6 easily. So with this approach, we were able to obtain the number of codes. In our case, with a boat, where we see our choices, and if the code is not a boat one, this is something that we found in standards in literature. For instance, for degree of 13, we see that we have much better improvement compared to something that is already used. And sometimes the differences are very small. In this case, we give the two proposals. And there are some differences in order. Differences in order are important because, for instance, here we could use this up to order 762. And like I said, when you have when the order is even, it means duplicate root, and perhaps it is optimal for very, very specific situation. Interesting part for 16 bits. Here are 3 standards that are present, and here we have a different values of m. So that is 512, 124, and so forth. And we do 2 proposals. One, they have the same values, the same value of SD. The only difference is that this one has order of 7161, so it is not applicable above this order. And this guy is already mentioned in some publications, which showed us that we are on the right way to attack the 24-bit. Now, like I said, with the increasing of the complexity, the calculations were getting more and more difficult. We did also for 17, 18, 19 degree, but at some point we tried to find some approach for 500 and for 24. Because for 24 we have standards, so these are the results for 17, 18, and 19. For 24 we have standards, and these standards are defined in 5G specification. The standard polynomials are these 3 here. So what was our approach? Initially, we decided to find, let's say, the first 1,000 optimal polynomials for 512, and to perform the calculations to up to this value for only for them. And we stated this specifically in the paper because we were certain that there could be, as we will see, that there could be some other guys that are performing better. We see here that with our proposal, this one, 1CE467F, we are performing quite better than the standard polynomials. Another interesting thing to mention is that this second polynomial is already discovered and it is used in the flex ray standard. And this was also one indication that we were on the right track. Now, after publishing this paper, we started to think what could we do better. So we did basically 3 things. We decided to target only the specific 5G intervals. We decided to improve the calculation flow, and we were dropping the assumption to investigate on the top performance for m equal to 512. The first and the third are quite easy to understand. For the second, for the improved calculation flow, I will return back to this matrix. What we did was when we were shortening this matrix with we performed a shortening with 32 bits on a step with 32 bits. So in this way, we were able to count in the initial matrix the original dual distance distribution, the distance distribution of this H matrix minus 32, the original distribution of H shortened by 64 positions, and so forth. So this was done on one step. Of course, we didn't calculate it all possible combinations. We did this later on a refinement, but with one step, we were able to calculate a large number of dual distance distributions. So this was the major improvement, and for 11, for instance, for 11 check bits, this is the CRC-11 standard, and our proposal for the whole interval from 31 to 1717 is you see here that we have a minimum distance of 4. Minimum distance of 4 between 31 and 149. And here, for the standards, we have minimum distance of 4 between 31 and 53. So in this interval between 54 and 149, our polynomial is dominant. And of course, the order of the polynomial, quite importantly, has to be larger than the interval that we investigate in, and in this case, it is so. So, what were the results? We for 24 check bits, we managed to propose several polynomials, and here A, B, and C are the 3 standards of 5G specification. So we have from minimum distance 6 here for from the interval from 16 to 915. And for instance, for the best interval, we have from 55 to 541. So we are seeing that here for interval of almost 400, we have minimum distance that is with 2 larger than the best standard polynomial. Saying this, if we are comparing this polynomial with that one, it is let's say better in more than 90% of the cases, but it is not better in all cases. So when the n is quite large, there are some cases when this one is slightly better than that one. This is in the essence of the CRC codes. If one code is good or extremely good in one interval, it performs poorly in another interval, and it is very difficult to find the right balance which CRC code has to be used. So these are about the results. What are the current plans? We're discussing some ideas attacking 32 bits, CRC with 32 bits. We are also looking for CRC codes with some special construction to detect error in verification part. And one very, it could sound obscure case, but there are some CRC codes of odd weight that are performing quite well in certain intervals. We'll be quite happy if we find a way to describe these codes. So having CRC code of odd weight doesn't mean exactly that the minimum distance is odd. In this case, we see that it is also in my PhD work that there are some examples of CRC codes with minimum distance 4 and odd weight. So odd weight does not imply that the minimum distance is odd number. Of course, if CRC code has x plus 1 as a factor, so if CRC is with even weight, it implies that it has even minimum distance. So basically, these were the things that I wanted to share with you.
Thank you very much, Peter.
Do you have questions?
While we wait for the other people, go ahead and raise your hand if you have a question. Peter, I'd like you to, can you tell us a little bit more about the process of using the dual code and the McWilliams identities to find the distance of the primal code? And
yes,
and specifically, how do you, so you're not just finding the distance of the primal code, you're finding the distance of sort of a sequence of shortened primal codes. Is that correct?
Yes. Actually, what we are doing is in this matrix. First, if we want to shorten the code with a number of positions, we are doing this on this matrix. So we are cutting the number of columns that are on a right side. So if the code is shortened by one position, we're cutting one column. If the code is shortened by more positions, we're cutting the corresponding number of positions. Then we are getting the matrix H. This is the matrix of the dual code. And we are performing the counting with a gray code. Using the gray code is convenient way to perform only one operation and to count the weight of the next word.
Can you explain a little bit more about what you mean by counting with the gray code?
The gray code is a code that you have some word, and then you are adding only one row, and you're getting the next word.
May I help?
The function of the gray code, yes.
Actually, gray code is the name of ordering of binary words of length n in such a way that neighboring words differ in only one position.
Yeah,
If
I think that's that part. I understand what a gray code is. I'm just trying to understand how you're employing it to do this calculation.
Okay, we use this in the following way. We have obtained a code word, and then to obtain the next one, we just add to it only one row from the generator matrix.
Oh, okay.
That's it.
And you use the gray code to index
Just to
which rows
order
you're adding.
words in the code, nothing else.
I see. So it's a way of ordering the way that you consider all the code words.
Yeah.
Got it. Okay. So so you actually go through the entire dual code and compute its distance spectrum by finding the weight of every word. And the way that you organize your pathway through every code word is by that limits your computation. You add one row at a time.
Yeah.
By the way oh, that's beautiful. I'm so glad. Okay, I get it now. And that's really neat. Okay, so you actually exhaustively go through the code, one word at a time, compute the code word, find its weight, and then thereby compute the distance spectrum of the dual code.
Yeah.
And the reason why you're using the dual code is because it has fewer code words than the primal code.
Yes.
And then once
Yes.
you've got the dual code distance spectrum, you use the McWilliams identities to get the distance spectrum for the primal code.
Yes.
Yes.
Okay, wow, that's really useful. Thank you very much. Do we have, I'm gonna let somebody else ask a question if they want to before I ask my next question. So do we have any questions from the audience? Hung Jae, do you have any questions? Okay.
Sorry, I think I have exactly the same question as you did. So
Okay, good. Okay, well, that was a good, can I ask, when you go back to your conclusions and you have the three things that you're going to do next, the middle bullet, is that related to what we were talking about? So you're finding, basically you find the CRCs that by themselves have the most favorable distance spectrums, looking over the entire interval that you're interested in. And then as a side hustle for us, you gave us the best CRC code from that perspective for a particular length that Jacob and I were interested in. I'm really grateful for that. So what I'm wondering is, are you interested in this idea that maybe the best distance spectrum of the CRC code by itself isn't enough to tell you about how it will perform in conjunction with the polar code? Because there's sort of a mapping of, you have a certain error pattern of a certain weight, and you're trying to make that the weight of the error pattern as large as possible. But once you make the error, that creates an error in the CRC in the entire code word. But then that creates a different code, a neighboring code word of the polar code. And if that neighboring code word in the polar code is far enough away, then that's not really a concern. So you're actually, there might be other code words that have more weight or whatever that would seem like they would have been a less of a problem for the CRC code. But because they end up producing a polar code word that is a nearby neighbor, they could actually be more of a problem. Do you see what I'm saying? And is that interesting to you guys?
Yes, it is interesting. The knowledge that we are missing is exactly how the polar code is used, because we have N and K, but let's say how the values of K vary. What is the typical pattern of for K? And if we have more information, more practical information on the polar code, perhaps we can make better CRC constructions.
In other words, how particular patterns, particular input words map to output words.
Yes.
Yes, and what are the values of K?
I have an answer to that
This
question.
type of things.
Go ahead, Amael.
I was actually going to ask the same question. That's why I waited for Professor Wessel. But there are in the standards, just as you can find the current CRCs, you also can find a list that order the rows of the polar codes that are to be used and standard values of K. I think 32 is a very common one. For the 5G standards, there are for the timing signal, the signaling system, they use polar codes, and there's a very thorough list of how it is used. So basically, you find exactly what the generator matrix would be, and drawing from that, it'd be possible to target the search for those specific matrices. Of course, like if anything changes, you will need to change the whole scheme.
Right. So, I think I can say another thing to clarify what Sanka and Peter, when you're talking about the input-output characteristic, I think what Amael is bringing up is that you need to know what the value of K is, and you also need to know which are the n minus K frozen bits in order to understand the pattern. Is that what you mean?
Yes, this is part of the thing, yes.
Yeah, so I mean, we can all agree that it's complex. You know, even to figure out what problem is you're trying to solve, we have to look at the standard very carefully and then work it out. But I think that, I mean, to me, I think that might be even more. So I understand that you're going to larger and larger CRC sizes because the standard calls for a 24-bit CRC. And so you've got to look through that entire space of 2 to the 22 possible CRCs to try to figure out which would be the best 24-bit CRC. But it might be the case that actually 24 is too big anyway. Some of the work that Jacob's been doing indicates that maybe, you know, that trade-off points to a smaller CRC so that the search space might actually be quite manageable, and that we could do this more of a bespoke or customized search that would include an understanding of the connection between the polar code and the CRC. I just think that's an interesting direction.
Yeah, I agree with this. It could be that we focus on some small dimension and find some optimal solutions for this.
So does anybody else want to go ahead? Yeah. Okay, so do we want anybody else? Darius, did you have any questions?
No, it's great talk. I enjoyed. Thanks.
Thank you very much. Okay, so I think we might have gotten through our, I'm sorry if I think I took the questions away. I asked the questions that some of our other participants were getting ready to ask. So anyway, I'd like to thank you again, Peter, and thank you, Sanka. And we're excited to continue exploring, you know, finding out what is the best CRC that we can use for a polar code. I think it's a problem that is of great practical interest today. So thanks a lot, guys. So why don't you stop sharing your screen, Peter, and we'll go to gallery mode. And I'm going to ask everybody to turn their cameras on. Here,
just one moment, please, because okay.
Oh, yeah. Okay. There. So if everybody goes to gallery mode, and we can all give a round of applause to Peter. So I'm going to put my virtual clapping hands up there, and thank you very much, Peter. I really enjoyed your talk, and I think that it's especially important to know about the I think, you know, I think there might be really interesting work to do using your tools, like I'd like to mention to my group that this idea of finding the distance spectrum of the dual code and then using the McWilliams identities to back out the distance spectrum of the primal code. I think that's a quite an interesting way to approach the problem, and theoretically deep. And we might want to think about doing that to not just the CRC code, but the concatenation of a small CRC code and the polar code, or applying it to the polar code, you know, so that especially for some of the low rate polar codes that we're looking at, this could be really interesting. As we've discussed in our group, if we know the distance spectrum of the polar code, then we'll be able to bound what is possible with the expurgation that is caused by the CRC. And then we'd be able to make some firm statements about why we're seeing, like currently we're in this position where we know how to find exactly the right CRC for a convolutional code. And it does better than the existing polar code CRC combinations, but we're not sure if the CRC for the polar code is really as good as it could be. And that's where we're hoping to work with Peter and Sanka and get to the bottom of that. But I also think that there are approaches, we could use Peter's approach of the McWilliams identities to get a bound on what's possible with the polar code and maybe say, well, you know what, we can see from the distance spectrum that even if we could expurgate with the perfectly optimal CRC, the distance will never be as good as what we're getting with the convolutional code. And then we can relax and not worry about it. So I think there's this talk has opened up some really interesting directions for us. And I think it could be really exciting. So I'll stop talking. Thank you again, Peter and Sanka. And it's nice to see, I see you have some colleagues there so that we're having a really global seminar. And you can always check our webpage. We're running about every 2 weeks. So our next seminar actually is going to be in quite a different topic. Jonathan Nguyen from our group is going to be talking about his work, comparing different approaches to a hybrid modem that does both radio frequency and optical frequency communication at the same time, whether or not it makes a difference whether you have a single code that's operating across both physical media or two different codes, one for the radio frequency and one for the optical frequency. So that'll be in 2 weeks. We'll have that link up soon. And then we'll just keep on bringing in talks about every 2 weeks. So thanks a lot, Peter and Sanka. And I guess with that, I'll let you guys go. Enjoy the rest of your Friday and the rest of your weekend. Bye-bye.